What's going on, guys? In this section we're going to finish up simple linear regression. So we're going to learn how to do t-tests, confidence intervals, and prediction intervals. So last video we were given the age variable, and with it we were asked to predict height. So in doing so we found the two parameter estimates of beta 0 and beta 1 to be 28.695 and 3.261. And then with those numbers, we were able to form predictions and then find the residuals to estimate the total model performance. But our parameter estimates of 28.695 and 3.261 are just estimates from one sample. So what if I said that the true population parameters were instead 30 and with a beta 1 value of equal to 3? Well, it turns out that if we take a bunch of samples, so here's sample 1, and we found beta 0 to be equal to 28.695, and then we found our beta 1 value to be equal to 3.261. In our second sample, we could find that our beta 0 value is equal to 32, and our beta 1 value is equal to 2.9. And then if we keep doing this, so we keep taking samples and finding our coefficient estimates, it turns out that if we add our coefficient estimates together, so for beta 0 we do 28.695 plus our 32, and then plus all the remaining samples, and then divide by the number of samples we took, this number will approach the true population parameter of 30. And then the same thing holds for our beta 1 parameter. So if we add up all our estimates, so 3.261 plus 2.9 from sample 2 plus sample 3, sample 4, sample 5, so on, divided by the number of samples that we took, this number will approach the true population parameter of 3. Now these true population parameters, so say we knew that it was 30, from each sample, if we take all the estimates, it turns out these estimates will create a normal distribution. So we might find that 95% of our coefficient estimates will be within a certain range, and we'll learn how to do that this video. And then the same thing holds for our beta 1. It also forms a normal distribution of beta 1 values centered around the true population parameter of 3. Two-tailed test. So last video we found how the model was performing as a whole using residual standard error and R-squared. But now we're going to learn how to find whether an individual predictor is performing well and whether or not it has an effect on the outcome. So to do this we can use a t-test. So for a t-test, we're going to form a null hypothesis, which is that our beta 1 parameter is equal to 0, or our alternative hypothesis, where our beta 1 parameter is not equal to 0. So our alternative hypothesis is what we're trying to prove. So we're setting it equal to 0 because if our 3.261 value was instead equal to 0, it's essentially saying that age does not affect a person's height. Because no matter what age you inputted, if the parameter estimate was 0, you would get the same height. So to do a t-test, we first have to get our t-statistic, which is going to be equal to our observed value minus our hypothesized value over the standard error. So our observed value is going to be our predicted beta 1 parameter. Our hypothesized value is just going to be equal to 0, and then divided by the standard error of our beta 1 coefficient. So our predicted beta 1 we already found to be 3.261. And then our hypothesized value is going to be 0, and now we have to solve for the standard error of beta 1. So the formula for the standard error of beta 1 is going to be equal to the square root of the mean squared error times 1 over the summation of x minus x bar squared. So mean squared error we solved for last video, and it's just equal to summation of our observed y's minus our predicted y's squared, or the sum of squared errors, divided by our n minus p minus 1. And we got a value of that equal to 5.4348. And then times 1 over the summation of x minus x bar squared, which we found to be 46. We take the square root of it, and we get a standard error for beta 1 equal to 0.3437. So if we do this out, we get a t-value equal to 9.4879. So we got our t-values, and now how do we know if it's significant or not? So now we create our critical score. So say we're using a 95% confidence. So if the absolute value of our t-score is greater than our t-critical value, then we reject the null hypothesis. So what this is saying, so if we have a normal distribution, it's saying if our t-score is greater than our critical value, so it's going to be if it's at the 0.05% on this side, 0.05% this side, because it's a two-tailed test, then we're going to reject our null hypothesis. So here's our 0 value. So if it's very far away from 0, we're going to reject. So we can find our t-critical value. So we're using 90% confidence. So that means our alpha value is going to be equal to 0.1. Now for a two-tailed test, since we find if it's very far positive-wise or negative-wise, we're going to end up doing this 0.1 value divided by 2. To get a value of 0.05, which we're then going to use for our t-table. Now if it was a one-tailed test, this alpha value will stay 0.1, and we're going to solve for one-tailed test next. So we're going to do alpha as 0.1 divided by 2 to get 0.05 for our table, and then our degrees of freedom, which is going to be, we had 4 observations minus our 1 predictor minus the intercept, so we're going to get 2. So we're going to use 2 degrees of freedom at 0.05 alpha to get a value of 2.92 for our critical score. So 2.92. So if the absolute value of our t-score, which we found to be 9.49, is greater than 2.92, we reject the null hypothesis. So what this means is our predictor x does have an effect on the dependent variable y, or that age is an important predictor in predicting a person's height. Now moving on from two-tailed tests, we can do a one-tailed test. So say we're trying to prove that our true population parameter is greater than 3. So our null hypothesis would be our beta 1 value is less than 3. And our alternative hypothesis, or what we're trying to prove, is that our beta 1 value is greater than or equal to 3. So this is going to be a right-tailed test. So our rejection region is going to be over here on the right. And if we're doing 90%, it'll be right here. We'll call this our rejection region. So anything less than this value will be fail to reject. So we're going to find the t-score in the exact same way. So our observed, which was 3.261, minus hypothesized, now we're going to use a value of 3, divided by the standard error, which is still the same as 0.3437, and we're going to get a t-value of 0.75938. So if our t-score is less than our critical value, then we failed to reject. So we need our t-score to be greater than our critical value to reject. So let's find our critical value. So the degrees of freedom is still going to be 2, 4 observations minus our 1 predictor minus the intercept, and then we're using a 90% confidence interval. So we're going to get a critical value of 1.8856. And then we got a t-score of 0.75938. So since this number is not greater than the critical value, we can say that we cannot be 90% confident that the true population parameter of age is greater than 3. Confidence interval for predictor. So we found our estimated predictors, so 28.695 and 3.261. So if we want to find the range for where the true population parameter lies within a certain interval, so say we want to find a 90% confidence interval for our beta 1 parameter of 3.261. So how we do this is we center it around our value, so 3.261 plus or minus, and then we add our t-score, which is going to be our alpha over 2 with n minus p minus 1 degrees of freedom, and then times the standard error of our parameter. So with this we can find the range that our true population parameter lies within 90% confidence. So if we use our t-table, so our alpha over 2, so we're using 90% confidence, so our alpha is going to be 0.1 divided by 2, so we're going to get 0.05, n minus p minus 1 degrees of freedom, so 2. So 0.05, 2, and we're going to get a t-value of 2.92. And then times their standard error of beta 1, which we already found to be 0.3437. And then plus or minus our 3.261. And we're going to get a range of 2.257 to 4.2646. So what this is saying is from our sample where we got an estimated parameter of 3.261, we can say within 90% confidence that the true population parameter falls within the interval of 2.257 to 4.2646. And then we can do the same thing for the intercepts. So the only thing that's going to change for the intercept is the standard error. So we're going to be using the standard error for the beta 0 parameter. And plus or minus the parameter estimate, which is 28.695. So if we're doing 90% confidence, we can use the same t-value of 2.92, and then times our standard error of beta 0, which we found to be 2.076, and we're going to get a value of 22.633 to 34.757. So we can say with 90% confidence that the true population parameter falls within the interval 22.633 to 34.757. Prediction interval versus confidence. So just like how we were able to form confidence intervals and use t-tests in our parameter estimates, we're also able to use confidence intervals on our predicted values. So say we wanted to enter in x is equal to 5, or someone that's the age of 5. Can we get a confidence interval or a range of predicted values for when x is equal to 5? So first we're going to find our predicted value, so 28.695 plus our 3.261 times 5, and we get a predicted value of 45. So what a confidence interval is saying is that what's the range within 45 where the true population parameter lies. So say we're doing a 90% confidence interval, so we can say within 90% confidence that the true population value for the mean when age of people aged 5 falls within a certain range. So let's say this is our prediction line, which we get from 28.695 plus 3.261 times our age. So here's our age, here's our height. So with our confidence interval, so we're starting with x is equal to 5, and say within 90% confidence that it falls within this range of height. So we can do the same thing for when age equals 6. It will fall within this range. And then when 7, it'll fall within this range. And what we're left with is if we connect these dots, we can form a range of predicted values for which the true population parameter lies within. So we're going from a sample to the population. Now a prediction interval, the only difference is with a confidence interval, we're taking the mean. So it's saying that everybody age 5, their average height falls within this range. Now a prediction interval is saying one observation. So let's say if there's one person age 5 and we want to find the 90% range, so we want to find 90% confident that the true population predicted value for when someone is 5 years old and their height would be, let's make our prediction line again. Now the difference is it's going to be wider than our confidence interval, because confidence interval is the mean of age 5. Prediction interval is only one observation of age 5. Now what do they share in common? So both of these curves, they're not straight lines. Instead they're curved inwards, or they're concave in if you want to say, and they reach their skinniest point of when the predictor value is at their mean. So predictor value here was age. So when someone's age 5, they share their smallest confidence interval and prediction interval. And now we'll be able to solve for these two lines numerically. So now let's solve for our confidence interval for the prediction. So our formula is going to be predicted y plus or minus, it's going to be our t-score of alpha over 2, and then n minus p minus 1 degrees of freedom, times our standard error of our confidence interval. So it's very similar to what we've been doing, just we're going to have a new formula for the standard error of our confidence interval, which is going to be equal to the square root of the mean squared error times 1 over n plus x minus x bar squared divided by the summation of x minus x bar squared. So let's say we want to find the confidence interval when our predicted value is 3, or when x is equal to 3. So what we're going to enter is our square root of our mean squared error, which we already found to be 5.4348 times 1 over n, which is 1 over 4, plus, and then our x value which we're looking for, so our predictor value is going to be 3, minus the mean of x, which is 5, and then divided by the summation of x minus x bar squared, which we found already to be 46. And with that, we're going to get a value of 1.3525. So now plugging into our equation, we're going to multiply it by our t-score. 25 times our t-score, which is going to be our alpha over 2. So let's say we want to do 95% confident this time. So alpha over 2, so it's going to be 0.05 divided by 2, so we're going to get a value of 0.025, and the degrees of freedom is still just 4 minus 1 minus 1 for 2. So we're going to get a t-score of 4.3027. And then our predicted value, if we just plug in 3 to our formula of 28.695 plus 3.261 times 3, and we get a value of 38.478. So solving, we get a confidence interval range of 32.655, and then an upper bound of 44.301. Okay. And then we do the same thing for our prediction interval. So the only thing that's going to change is the standard error again. So predicted y plus or minus our alpha value over 2 with n minus p minus 1 degrees of freedom times our standard error of our prediction interval. So standard error of our prediction interval is going to be equal to the square root of our mean squared error times 1 plus 1 over n plus x minus x bar squared divided by the summation of x minus x bar squared. So the only difference here from this and the confidence interval is this extra 1 term. So that's another way of saying that the standard error of the prediction interval is just equal to the standard error of the confidence interval plus this 1 mean squared error term. Okay, and solving, so mean squared error, so we found to be 5.4348 times 1 plus 1 over 4 plus x minus x bar. So if we use the same number, so if we use x equals 3 with a 95% confidence, so 3 minus the mean of x, which is 5, squared, divided by the summation of x minus x bar squared, which we found to be 46. We take the square root of that, and we're going to get a value of 2.6956. So it's the same t-score as last time, 0.025, 2 degrees of freedom, 4.3027. So 4.3027 times our standard error of 2.6956, and then plus or minus our predicted value, which we already found to be 38.478. So they both center around the same value, it's just the prediction interval is going to be wider. And we're going to get a range of 26.88 for a lower bound, and our upper bound is going to be 50.076. So this is saying if we take one observation that has the age of 3, we can expect their true value for height to be between 26.88 and 50.076. Okay, so that's all I got. I hope you enjoyed.